For the Module 7 homework, I'd first like to call your attention to the text box at the top where it says, although the formatting has flubbed a little bit on my copy here, you should be able to provide a thorough definition of a solid, liquid, and a gas. So this will be a collegiate level definition. I want you to use your own words. I don't want to see something from Wikipedia, and I don't want to see something that came out of my lesson. What I want you to do is use all of the key words that you know in order to provide that thorough definition. If you'd like to pre-write it, send it to me for review. I'm happy to do so via the Canvas inbox. Remember, I can't get back to you instantly, and I will need some time to review it and then provide my comments. You should also be able to discuss what STP means. Now, some students like to be cute and call it a gasoline additive. However, you should understand that in the context of this course, that STP means standard temperature and pressure. Standard temperature and pressure is 0 degrees Celsius and 10 to the 5th pascals. Now, you also need to know how to convert between pascals and atmospheres. So 1 atmosphere is equal to 101,325 pascals. So that would be 101.325 kilopascals. Now, you should also be able to use Boyle's, Charles, and the ideal gas law. So Boyle's law is P1V1 equals P2V2. Charles' law is V1 over T1 is equal to V2 over T2. And the ideal gas law is PV equals nRT. Now, you should also be able to find the molar mass using the ideal gas law. There are practice problems within the classroom for that, as well as be able to match solid cubic units with the effective number of atoms in each cell. And there are pictures of those solid cubic units in the lecture. And also the comprehensive question below. Now, this comprehensive question, you should also be preparing for the final with these comprehensive questions, but we'll go over it. So what is the molar mass of a fictional gas that occupies 1.03 liters at temperature is 19.9 degrees Celsius while exhibiting a pressure of 87.9 kilopascals if the gas has a mass of 8.51 grams. Well, this fictional gas, the first thing we're going to do is use the ideal gas law in order to find out how many moles of this gas we have. So the ideal gas law being PV equals nRT. R is our ideal gas constant, 0.08206. Remember, the units for that are liters, atmospheres per mole Kelvin. So we need to match these units with our given quantities. So the pressure that we're given is 87.9 kilopascals. We need to convert that into atmospheres. So 1 atmosphere is 101.325 kilopascals. So that'll be my pressure. The volume is probably the easiest thing we were given, 1.03 liters. And that's going to be equal to N, which is the moles, which is what we're looking for, our R value. And then our temperature. Now, the temperature, we do need to have that in Kelvin. Remember, we take our Celsius value and add 273.15 in order to get Kelvin. Now, that's going to get messy in a hurry, so I'm going to move some of that over here. When I perform the calculation with my pressure, so let me just reveal that real quick, 87.9 divided by 101.325, I get a value, and then I multiply that by 1.03. So the left side of my equation becomes 0.89353. I'm going to give you all of the digits here so you can double check your problem solving as well. And that's going to be equal to N times. So I'm going to take my R value and multiply it by my temperature. So when I add 19.9 to 273.15, I get 293.05, and I'm going to multiply that by 0.08206. So the right side of my equation is N times 24.047683. Now the N is moles, M-O-L-E-S. And in order to get these moles, I need to take this value, this 0.89. Oops, I put a 0 in my calculator where it didn't belong. 0.893530718. And I'm going to divide it by that 24 value. And I get the number of moles is 0.0371566. Now again, I'm not rounding yet. We don't round until the very bitter end. So the question asked us for the molar mass. Well, the molar mass is going to be grams per mole. We have a mass of 8.51 grams, and that mass, 8.51 grams, contains 0.0371566 moles. So when I divide these two values, I will get the grams per mole, and that is 229.03 grams per mole. So now I look back into my original question, and all of those numbers have 3 significant digits. So I can only record 3 significant digits. So I would record 229 grams per mole. That's 3 significant digits. Number 2, what is the pressure of 6.05 grams of nitrogen gas at a volume of 4.2 liters, and the temperature is 22.3 degrees Celsius. Well, we're going to be using the ideal gas law for this as well. We need to convert this temperature into Kelvin by adding 273.15. And let's see, we would get 0.45. 295.45, capital K for Kelvin. We are looking for the pressure. The moles we're going to calculate. So we're told we have 6.05 grams of nitrogen gas. You need to remember that nitrogen gas is diatomic, so its chemical formula is N2. And 1 mole of N2 has a mass of 28.0 grams. You get the mass of nitrogen, multiply it by 2. So then we would get our moles of nitrogen. And I get a value of 0.21607. I'm going to stop it there because I'm just going to leave it in my calculator. So the only thing we have left in order to use our ideal gas law is R. Now, R is our universal gas constant, or our ideal gas constant. Therefore, R is just going to be the same as in the previous problem. So P is what we're looking for. I'm going to fill in. I have my V at 4.2 liters, and that is going to be equal to our N, 0.21607, but this value is actually just still in my calculator. R is the ideal gas constant, and that is liters, atmospheres, mole, Kelvin. And then T is going to be 295.45 Kelvin. So the right side of my equation, I just multiply these 3 values together. I get 5.23857. It keeps going, but watch how the moles cancel and the Kelvin cancels. So we are left with liters and atmospheres. So the left side of my equation hasn't changed. I have P times 4.2 liters. I divide both sides by that 4.2 liters to get my P alone. That cancels out the liters, and I am left with 1.247 atmospheres. I'm going to scroll back up to the top. We have 3 significant digits in my grams of nitrogen, 2 in the volume, 4.2. Therefore, I need to only have 2 significant digits. Now, I thought there was something against sig fig sting. Record your answer to the 100th place. Okay, so that's going to actually be 3 significant figures, but that's okay. So here's 1, 2. This is my 3rd significant digit. I look next door to find out, do I round up or truncate? And the answer is I'm going to round up. So 1.25 atmospheres is what I would record. And now for the comprehensive question. So what is the percent yield? So we're going to throw back to Module 5 of a reaction of oxygen gas. You have to know that oxygen gas is O2 in a vessel that has a pressure of 782 millimeters of mercury, a volume of 750 milliliters, and a temperature of 25 degrees Celsius. And that oxygen is going to be with 1.3 grams of solid aluminum, So don't forget the phases, and that will form aluminum oxide. So we're going to throw back to module 2 as well. What is the chemical formula for aluminum oxide? Recall that aluminum makes a +3 and oxygen makes a -2 ion. We can do our crossing charges, or you could use some brief algebra, whichever way you prefer. Just a quick review on the crossing charges, because a lot of students like that one. So what I'm going to do is when you have these mixed numerical values for the charges, what you do is you take the number of the cation, and that's going to become the subscript of the anion. And then the number of the anion becomes the subscript of the cation. So when I go to write this chemical formula, it would be Al2O3, and it specifically says it's solid. So when I go to write out this equation, and I like to start with my metal, I'm going to have Al solid plus O2 gas reacts to form Al2O3 solid. So the first question actually says to write the balanced equation. So you have to know all of those things. That's chapters 2 and 4, not 3. So to balance this actually becomes relatively easy in my opinion. I'm going to start with oxygen because it's going to be the trickiest one. It has subscripts on both sides. So I'm going to put a 3 here, which is going to put a 2 here so that we have 6 oxygen atoms. That's put a 4 in front of the aluminum. Now you can go back and do it the longer way where you count each atom each time, and that's okay if you need to do it that way. I'm showing you a faster way for those of you who are comfortable with it. So now we need to determine the moles of oxygen in the system. So this is number 1. To determine the moles of oxygen, we need to use the ideal gas law. So for number 2, this is going to be PV equals nRT. Let's gather our variables first. So the pressure is 782 millimeters of mercury. I'm going to need to convert that into atmospheres. And I know I need to convert that into atmospheres because our R value, the 8206. I can't talk and write at the same time, which makes this a little there. So we have to have our units for R, liters, atmospheres, mole, Kelvin. So we have to have all of our units match. So to convert our pressure into atmospheres, I need to divide by 760 millimeters of mercury. That'll give me atmospheres. Volume, the vessel volume was 750 milliliters. So you have to convert that into liters. That was module 1, 0.750 liters. This 0 is significant, and I know it's significant because this decimal place is here to tell me so. PV, let's see, N is what we're looking for. R is the constant, and T, the temperature, 25 degrees Celsius. You've probably used it enough that in your head you can go, okay, well, that's 298 Kelvin. 298.15 if we want to increase our precision. So now let's work this out. So we have our pressure, our volume, N is what we're looking for, R, and then T. So to work the algebra here, I'm going to take 782 and divide that by 760. I get 1.0289 for those of you keeping track. Then I multiply that by 0.75. So the left side of my equation becomes 0.7717, and that is going to be equal to N times the product of 0.08206 and 298. I get 24.45388. Now to get N all by itself, that means I have to divide both sides by this 24 value. So I'm going to take my 0.7717 and divide by 24.45 and all that rest of that stuff. And I get that I have 0.031557 moles. Now, because we are going to report this, I'm going to scroll up. Because the temperature that I used was not 2 significant figures because I added it, and now I have 5 significant figures, that is not going to be limiting. It looks like 3 significant figures so far because I'm here at 2. I'm determining the moles. I haven't used this yet. So I need 3 significant digits. So I have 1, 2, 3. Look next door. I'm going to round that up. So the answer to number 2 is going to be 0.0316 moles. Number 3, let's determine that limiting reagent. So although we recorded 3 significant digits for number 2, for the moles of oxygen in the system, because we need to use that value in a further calculation, I went back and grabbed all of the digits off of my calculator because we're not going to round in the middle here. In order to determine the limiting reagent, what I need to do is find out how many grams of our product can we make from the oxygen. So I'm going to use all of the digits my calculator had. Now I have moles of oxygen, that's where I'm starting. So I need to convert my moles of oxygen into moles of aluminum oxide. So I use the stoichiometry found in the balanced chemical equation. And that 2 is the coefficient in front of the product, and the 3 is the coefficient in front of the oxygen. And then I need to use the molar mass of aluminum oxide. So 1 mole of aluminum oxide. And what is the molar mass? Well, this is where you go to the periodic table and you find that aluminum has a mass of 26.982 grams per mole, and oxygen has a mass of 16 grams per mole. Now, if your periodic table says something slightly different, that's okay, because I will have a little bit of grace on the grading, so don't worry about that. So I take 2 times 26.982 and I add that to 16 times 3, and I get a molar mass of 101.964. So that's the molar mass I will use in order to calculate how much product I can possibly make. So when I perform this calculation, I take this value here, 0.03155573, and all the other digits that were in my calculator. I multiply it by 2, and then I multiply that by 101.964. And then I divide all of that by 3. So I get from the oxygen, I can make 2.145 grams of my product. Now from the aluminum, I'm just going to move this down slightly. I start with 1.8 grams of aluminum. That's what I was given in my problem. 1 mole of aluminum has a mass of 26.982 grams. So my grams cancel, I'm left with moles. Now I need to use that stoichiometry that's found in the balanced chemical equation. 4 moles of aluminum are required to make 2 moles of aluminum oxide. And then we use the molar mass again, so 101.964 grams of aluminum oxide for every 1 mole of aluminum oxide. So the grams of aluminum cancel, the moles of aluminum cancel. Oh, I didn't put moles here. Moles of aluminum oxide, I am left with grams of aluminum oxide. So to perform this calculation, take 1.8, multiply it by 2, and then by 101.964. You will divide that by the product of 26.982 and 4. And I get 3.40 grams of our product can possibly be made. That means that the oxygen is the limiting reagent in this problem. So what is the percent yield? Well, the percent yield is found by taking the actual amount that was obtained. So it's 100 times actual over theoretical. Now the theoretical yield is this value here. Now let's see how many digits our actual yield has. Oh, I used 1.8. It should have been 1.3. Okay, I revised my calculation, and oxygen is still limiting, but it would form 2.45 grams of of product with the correct mass of reactant, the 1.3 grams of aluminum. So my actual yield was 1.8 grams of aluminum oxide. That's given right here. My theoretical yield is 2.1 grams. So this percent yield is going to be 100 times 1.8 divided by 2.1, and I get 85.7%. That would be the answer to number 4. For the building problem from Module 7, the layer that we're adding is this introduction of how many moles of gas are there when we are given just these conditions, and then what is the percent yield. So we're going to be performing a limiting reaction analysis, a limiting reactant analysis with these conditions. So the first thing I'm going to start with, we've done all of these things in different videos. So I'm going to ignore those, and I'm really only going to focus on this part here. So I need to start with the balanced chemical equation. I still need the information from the previous parts. So C2H4 is what we determined the molecular formula was going to be. And the balanced combustion reaction is going to look like this. And we did this in previous videos. You can always look up on the other homework assignments for those previous videos. So now I'm going to do the gas part. I have 5 liters, so that's my volume. I have a pressure of 29.5 atmospheres, and I've actually gone back and amended this so that the temperature is 25.0 degrees Celsius. Okay, so my temperature is actually going to be 298.15 because I'm just going to use as much precision as I have and only round at the bitter end. Now the R value is constant, so we're going to use our ideal gas law, and we have our pressure, 29.5 atmospheres, with a volume of 5.0 liters. N is what we're looking for. We need to find out how many moles of gas we have. R is the constant, 0.08206. I'm just going to leave off the units. And then the temperature is 298.15. So to perform this calculation, I multiply 29.5 times 5, and I get 147.5. That's going to be equal to N times this value, 0.08206 times 298.15, and I get many digits in my calculator. I'm just going to leave them in my calculator, but I'll tell you I get 24.46618, and it continues. Okay, but that's as much as I'm going to write down. Then to calculate for N, I need to divide both sides by this 24.466 value. And that's actually, I just leave that in my calculator so that I don't have rounding error. So the N that I get is 6.0287, again, don't round yet, moles of oxygen. Well, what does that tell us? Well, now we can use those moles of oxygen in order to find out how much product we would make. So starting with this value that stays in my calculator, this 6.0287 business, moles of oxygen, I'm going to convert that into moles of my product. And in order to do that, I need the balanced chemical reaction. That's why I wrote it first. So these values come from here. So the 2 for carbon dioxide is 2 moles of carbon dioxide are produced for every, let's do yellow, 2 moles of oxygen that are reacted. So that's here, and I should have yellowed that as well. So that's where those values come from. So now I can convert those moles of oxygen into moles of carbon dioxide. Now, just to be thorough, because the calculator is doing the work anyway, I'm going to use the molar mass of carbon dioxide, which is 44.01 grams of CO2 for every mole of CO2. Now, just a very brief reminder. What I'm doing is going to the periodic table and finding that the atomic mass of carbon is 12.01. On my, I need to write that down. And for oxygen, I have 16.00 on my periodic table. Now, there are 2 oxygens in this molecule, so I'm going to multiply that 16 by 2, and then I add all of this business together, and I get 44.01. That's how we find that molar mass. So now I perform this calculation, and what that means is I'm going to multiply the values across the top. 6.0287 times 2 times 44.01 divided by 2, and I get a value of 265.32 grams of carbon dioxide. Now let's just double check these units real quick, our dimensional analysis. So our moles of oxygen cancel with moles of oxygen, moles of carbon dioxide cancel with moles of carbon dioxide. I am left with grams of carbon dioxide, which is what I was looking for. So That's convenient. We did the dimensional analysis correctly. So now we need to run through the other reactant. Now for the other reactant, I have 60.0 grams of my hydrocarbon. My hydrocarbon is C2H4. I found that in a previous step. I need to convert that into moles because 99% of the time you see grams, you need to convert it into moles. So I find the molar mass of this, and I find 28.06 grams of C2H4. Again, I'm taking the atomic mass of hydrogen, multiplying it by 4, and adding that to the atomic mass of carbon multiplied by 2. And that is 1 mole of C2H4 is 28.06 grams. So now I have moles of C2H4. Now I use the values in the balanced chemical equation, and remember the absence of a number in a balanced equation is a 1 and not a 0. And I need to convert that into moles of CO2. And then I use the molar mass, so 44.01 grams of CO2 for every 1 mole of CO2, in order to find out how much carbon dioxide could I make from that hydrocarbon. And the answer is I can make 188.21 grams of CO2. And I got that by multiplying my 60, this is actually a 60 times 2 times 44.01 divided by 28.06. And you should end up with 188.21. So that means my limiting reactant is the hydrocarbon, but that wasn't the question that was asked. The question was, what's the percent yield? So this is my theoretical yield. Now remember that percent yield is going to be 100 times the experimental value over the theoretical value. Now the theoretical value is this 188.21 grams. I feel like I might be off the screen here. The experimental value was found up here, 176.2. Was that an 8? 176.28. So that value goes here, 176.28 grams. And when you perform this calculation, you should end up with a percent yield of 93.7%.